you can take a look at what Bryn did here if you like. Just to be honest here, ladies and gentlemen, this is not a trigonometry warm-up, is it? It's an algebra warm-up, isn't it?
Yeah.
Like, did you ever have a trig thought as you were doing this? Like, not a one. Not a one. All you were thinking about is like factoring, fractions, cancellation, right? I know you have trig on the brain, and I put trig functions there, but... All right, did you do the second warm-up, though? Over here?
No, it's the same.
What?
It's the same thing.
Oh, it's the same thing? In what sense is it the same thing?
Are you sure?
If you replace A with sin X and
Oh, like you're looking for and making use of structure? Is that what I hear you say? Are you a mathematician? Is that what I hear you say? Okay. Do you like to reuse structure and make use of structure? I think that's what I heard you say. All right. So it is the same problem in a little high level way, right? Isn't it? If you work this problem, you'll feel the same things you felt as you did the first problem. In fact, if you wanted, that even suggests a way into this problem. Like if for some reason this is easier for you, or less intimidating, or whatever, well, feel free to do this. Do the algebra. You'll get A when you're done, and then you could take this problem. You could take this problem into A/B land, and then say, oh yeah, A was sin X. You know, you could actually do that if you wanted to, right? If that scares you, use substitutions to make your life look simpler. I will say, having a good algebraic background will be of good service to you in this particular unit in ways that wasn't true in the previous two units. Okay, so we are going to do more trig. And the title of this unit is Trigonometric Identities and Equations. So we're going to be discussing kind of the high-level properties of these functions that we've been using for a while, but I'd like you to kind of back away, take a little bit of a higher view, and also maybe a slightly more algebraic view. We've had a very geometric view, Unit 4. In Unit 5, we had a very kind of graphical view, and now we'd like to come around, we'll still be talking about those things, but we'd like to lay on top of that a more algebraic approach in ways that feel like a warm-up way. In particular, you've already identified some ways that these functions behave on a global level. You've already noticed the odd-even behavior. You've noticed the reciprocal relationships, maybe. And I'd like to continue with that theme a little bit more and in depth. Notice that this is a little bit of a longer unit. Do you see it? Yeah. Okay, well, it's got to sustain us until the very end. So notice your test is not till January, and your IB problem, too. Look at the dates. Make sure those get in your calendar. We'll try, unless snow derails us, we'll try to take full of those dates. Notice also that we have 2 speed trig quizzes this unit. I think we've warned you about that. They'll be 3:30 and 3 minutes in length. Okay? Again, reminder that we'll be dropping one of those. So in the end, it'll only be like a 30-point quiz grade total, right? You'll have 4 of them, 10 points each. We'll drop one. So that's how that works. And there's also a prize for the person, any people, if there are, that get a perfect score on all 4 of them. So, moving smartly along, I have actually, I know it's a little hard to believe, but I do have like a photo to show you.
Oh, I'm excited.
Now, I have to admit, I did actually rig this one. Okay, it's always a road trip. I don't know. So I was in West Virginia, and there's like only one place to stop for food. It's at like fast food places like McDonald's. So we had to stop there. And while I was there, like I eat really quickly, so I was done. I was like, hey, to the manager, can I get that like thing that you know, the big pole that you use to like adjust the sign? So and then I went out there and I like adjusted the sign.
Oh, you
The placard, you know? Yeah. Oh, I see. And so then I adjusted all the letters that he gave me, like the pile of letters they use and everything. And then I took a picture of a beautiful clear blue sky on that day. And I put it into our PowerPoint. Again, as usual, for your educational enjoyment. Okay. So isn't that amazing? It's not as amazing as the other ones, which were all coincidence. But it is a good story. Okay, here we go. Let's talk about trig identities a little bit. We'll start today with just the fundamental identities. Again, the project here is to start realizing some like global things that are happening with these functions that we can make some observations about. And not just like make conjectures, but prove things that we think are happening to be true. So I actually have a gift for you here. A little early Christmas present coming to you. These are the identities I'm going to tell you today, but we're going to do some examples that aren't on here, so don't like just put your pencil away or anything. Actually, the heavy lifting I'd love you to do today is prove. I'd love you to prove all the things that are on this sheet, okay? Supposedly these things are all true. Many of them you already know, I think. Right? Look at these already. Scan down the page. These things you know what they might be.
Cosine squared plus sin squared.
Are these things you know?
Rather be English.
Alright, hey, whoa. I passed out papers for 2 seconds and I makes you go wild. I know. Okay, here we go. Listen. So I want to draw your attention first to the reciprocal identities. And how about the quotient identities? We'll throw them all up here at the same time. And again, even though they're in like finally in a box, whoa, they're in a box. I think, though, isn't it true, that you have already known all of these things. In fact, I've already made, as a teacher, I've already made the assumption that you know these things. Because when we were talking about how to graph cosecant, for example, I said, isn't that just 1 over sine? You were all like, uh-huh. But we didn't like actually stop to like maybe prove that that's true. It's not a very hard proof, which is why I think I made the assumption, and we all made the assumption that we kind of know why that's true. So could you prove it right now, though, please? And also the quotient identities. Just prove one of them. Pick one to prove here. And pick one of these to prove, maybe this first one here. And see if you can prove it. And by prove it, I mean from the definitions of those functions, right? So do you remember, for example, what the definition of sine theta is for the angle theta? Let's not maybe say opposite over hypotenuse. Let's say, what? Yeah, y over r, just so that we understand that theta could actually be any angle. So go ahead and prove that using that technology. And the style of your proof, I feel like, should go like this. Cosine theta equals what in terms of the definition? And what does that equal? And what does that equal? And then in the end, I want you to be like, and that's 1 over sine, right? That's the way this should feel. Does that make sense? And then do the same thing with one of the 2 ones in the box. You don't have to prove the ones I circled. Just prove one of these, and they all feel the same. And when you get it, just say, here we go. That's not very enthusiastic. Wait, you're going to go like that? You're going to miss the best. Did you prove them already? Go ahead. All right. So, these are very, very short proofs. Do the tangent one.
Oh, I forgot to do that one.
So the proof is not long. It really does only have maybe 2 blanks in it, right? Right? Done. Someone proved the quotient identity, one of them, in a similar manner. By the way, it doesn't matter which side you start on. You can make the chain of equalities go that direction instead. You want that next one? Okay. Go for it. Okay, yeah. Take it up. Again, I need you to start with like one expression, do some stuff, and end with the other expression. That'll be a proof. And if this is not a challenge for you, the next thing I'm going to ask you to do is to do Pythagorean identity. The first one, cosine squared equals sine squared equals 1. We're going to prove that in a minute, and see if you can beat me. See if you can beat us. See that. These are simple. Start this one. Prove that. Again, use the definition. You want a sticker? Congratulations. So, again, you're welcome. So this is what it feels like to, I think, prove these statements. remember that our project here is all about proving things in Factus Unum. We're gonna like prove tons of stuff. And at no time should you be like, the reason I believe this is because Mr. Chase told me. No. No, that's never appropriate in a math class. This is a sense-making discipline. Every single thing should lay on top of a very firm foundation, right? So we're going all the way back to definitions. We want to always let it rest on some other previous result that's been established deductively, right? That's the beauty of mathematics that we bring to the table that no other discipline does. Okay. And we also bring you, cat memes. I know, right? Did you see and appreciate the two proofs that were written up here before I make those go away? Okay. Just want to make sure you appreciate the work. So feel free to prove the other ones if you like. They're very similar though. So I don't feel like the need to do that in front of you. Have you tried to prove that first Pythagorean identity that sine squared of theta plus cosine squared theta equals 1? Try proving that again from the definitions of sine and cosine. See if you can do that. Just the first one for now. We'll worry about the other ones in a minute here. But the first one is not quite as trivial as what we just experienced a minute ago. The other ones were pretty quick, weren't they? Even doing like 2 lines of work felt like we were really pulling teeth. It was like, wow, this is like a lot of work. This one is actually kind of interesting. And maybe give it a try. Again, I might start by considering cosine squared plus sine squared. Don't say that it's equal to 1 yet. And see what it equals. Cosine squared plus sine squared. Work with it and see if in the end you get 1. That would constitute a proof. The radius is whatever the radius wants to be. It could be. It doesn't work. What if it's 5? Does it still work?
Well, now you do.
There are videos of me going.
I saw your concept. I retweeted it.
I haven't looked at it in like a while. What's it up to? 50,000.
I'm not. I've heard, yes. Wait,
alright, I need someone to put the proof up here. Who's got it? Who wants this?
It looks like no, that's good.
just the entire class just has to bring something every
Like well-formed mathematics. I think you thought the right way.
Well, Laura, I think that's a little bit too much.
Yeah, but I just call you why don't you put it up here? Why don't you put it up here? Can you write it like here? Yeah. Alright, here comes Jasper. Go look, it's done yet. Figure out your stuff. Feels good to prove things. Feels good to prove something that will last forever. You know what I'm saying? It's like eternally true. Even after you die, it'll still remain. You know? You'll have a legacy. Probably more than most people have proved it, but that doesn't mean you haven't, but we've like tapped into the collective eternal conscience. So I mean, yeah, exactly. Something like that. It's got a little weird. All right, so let's see if we can follow Jasper's work here. So cosine, the question is, what is cosine squared plus sine squared? And the answer is, oh, it's x over r squared plus y over r squared, which is x squared over r squared plus y squared over r squared. I think a lot of people got to this stage and then you combine fractions. So in the end, cosine squared plus sine squared is equal to x squared plus y squared over r squared. And then this is like a side comment or something over here. He's just remembering that by r, that was just like a quick shorthand we used when we first studied this and defined these functions. We said, oh, and by the way, r is just like a shorthand for like the radius, or you could say square root of x squared plus y squared, right? Or x squared plus y squared equals r squared. We need to remember that relationship. You'd actually need to invoke that here to finish this. So that's just r squared on top, he realizes, which then makes this just 1. By the way, does that also make us realize why these might be called the Pythagorean identities? Because what did you have to invoke there on the last step? You had to invoke the Pythagorean theorem, didn't you? So I hope, yeah, this, in fact, it doesn't work. You can't finish the proof unless you realize the Pythagorean relationship between x, y, and r. By the way, they could appear in these. It could appear in these forms as well. This first one, the second line here is gotten by just taking the first equation and dividing through by something. Cosine squared. Yeah? And if you divide the first equation everywhere by cosine squared, you get 1, clearly. Sine squared divided by cosine squared is tan squared. And 1 divided by cosine squared is secant squared, isn't it? And the third equation is gotten from the first equation by dividing through by sine squared. Okay? Now, keep in mind that these are important enough and ubiquitous enough that you need to recognize them not just in these forms, but in any other algebraic manipulated form that they might come to you, like these, right? So if you ever see like a 1 minus sine squared, you should be like excited. You should like, your little spidey sense should go off. You'd be like, that's cosine squared. Like, and you should have an irresistible urge to replace the 1 minus sine squared that you see with a cosine squared, right? Likewise, your spidey sense should go off if you see anything on this page. You should be like, ooh, I sense a relationship that I should know.
What is so
Manual.
Is there anything else you want to say about this? Let's see here. Good. So you'll get used to them. We'll hone and calibrate your spidey sense. Okay. As you do more of these problems, you'll like learn to recognize these things more and more in the wild. Well, you don't have the great power yet, but you'll get there. You'll get there. So I don't need to necessarily like linger on this slide. If you want to like rewrite these algebraically, all I did was just take the equations that are in the box and rearrange them in like every possible algebraic way I could think to do them. Right? So just recognize them whenever things are on different sides of the equation. So those are the Pythagorean identities. I think you knew the first one before, maybe. Maybe you'd studied that, at least the first line. You'd seen that before and possibly even proved it in your life before this. I don't know. Are we having fun yet? Let's practice your identities that you know so far by simplifying the following expressions. And now, I'd like you to not just kind of like pull on your algebra skills, hopefully you have those, but also to pull on your new trig identity skills that you have, right? Let's bring both into play. Ready, go. I'll give you a minute to do them all here. See how far we get. Yeah. could. If you can avoid, I mean, you can start using, yeah, I mean, absolutely you could. It would work. Yep.
No, I took a picture. I swear I just showed you.
That's nice. Cosine of sine. Yeah. That's just one. Okay, so that's cosine of sine. That's 1 over cosine. Cosine, 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 sine.
My second one.
Who wants to stay?
That's cosine of sine, right? And secant 1 over cosine.
Oh wait, okay. Right? I would have gotten that on a quiz. Oh, so it was 1. Oh. Well, that's 1 over sine times sine.
It was 2.
It's tan squared over.
Wait, 10 times 4.
I didn't mean to disappoint you, but.
Oh. Yeah, we're giving credit for her mathematical sense. So.
My attention span is too much. No, because science squared.
Sorry,
That's not supposed to be.
Whoa.
That's going to be 2.
Angela, you got a sticker. Good job. It is 2. Yeah. You could
2 sine.
you both could improve your penmanship. I'll just be honest. That's true. But it's right. It's right.
Whoa. That's just, you can't, that's,
You can't say that.
see, that's
No,
minus 2.
Is that two? But it's we're working on it. It's good. So she just expanded all that out. She saw some stuff went away. Yeah. I like that. And then I need something for C. Anyone willing to do it? C is a little tricky to have.
Oh my god.
Think about tan squared and what maybe you could replace that with. Something we talked about. And then just remember your algebra too.
I understand. Oh, right. I get it. I got it, guys. I understand. Yeah, because it's like.
You want me to do this one? I just mean I don't know. There are a lot of people who are like going crazy on this one. All sorts of weird stuff. The first thing I might recommend is replacing tan squared by something. I will just give you the first step at least. What would you replace tan squared with? Secant squared minus 1? Because, I don't know, it's on the sheet. We proved it. And then I might think again about algebra and notice the structure. Make use of structure, right? Doesn't that numerator have the form like something squared minus 1?
Yeah. This one. Secant
Yeah.
theta.
Right?
Just secant theta.
So the numerator has the form something squared
It's
minus
secant
1.
squared.
from the one of the Pythagorean, the second Pythagorean identity.
Wait, Mr. Chase, we got a screen.
Oh, you want to do it?
Hey,
You're on.
I will be buying
Here comes Cheyenne. Hailing from table 1. Got his start over on the left side. He's made a name for himself.
got it, yeah.
He's coming out of a rough year, injury last year.
Wow. Feeling it.
Looks like he's factoring getting rid of. Moving in strong.
That's not a plus, that's a minus.
It's a minus, everybody, he says. We'll take that play under review.
Oh, wait, you're right.
Do you see what he did just there? Did you see that?
Lost out 2 numbers, wow.
Did you see how he used it? An identity that he knows from algebra, that a squared minus b squared equals something. Yeah, he used difference of squares to help him out there a little bit. Isn't that nice? So in the end, someone could ask you like, hey, this is a function, f of theta, graph it. What? And you'd be like, you'd do the work, you'd be like, oh, I'm just being asked to graph secant. It's just secant theta. That's a helpful thing to say. Or someone said, here's a function, f of theta, evaluate it when theta is pi over 3. Realizing that this is really just secant theta would be a favor to you if you just knew that those were the same thing. Yeah.
You try and like make an equivalent function, but like since it's written in fraction form in this case, would stuff like be aware of like restrictions in the domain?
That is a very astute observation. We'll see. There might still be another restriction besides secant. Like there might be another hole somewhere or something. Is that what you're saying? We have to think carefully about this denominator maybe. Where is tangent undefined? At pi over 2 and every integer multiple after that of pi. And secant is, so we might actually have other places where it has like holes, right? Yeah, this canceling out might have like been a hole actually in the graph of that. You're right. So we do have domain issues. Just for the sake of time, let me run through this example with you, and I'll show you one way. So I would challenge you to come up with a second way to do this problem, okay? So let me just say this before we take a look deeply at this question. This is actually a question I've given you before. Like I think I even gave it to you, or something very similar to it. On one of your quizzes in the last 2 units here, maybe early on when we first discussed sine and cosine and all their definitions. I think we gave one like this to you right away, early on. But this time, I'd like to take an algebraic approach and use some of the identities we've been working with. So if I know the tangent of an angle, can I find the sine and the cosine? I think I can. In fact, there's a relationship we were just using a second ago between tangent and secant, which I could take advantage of, right? Would we say that 1 plus tan squared is equal to secant squared? Isn't that a thing? I don't know, it's on the paper, and we proved that it's true, so it must be true. Okay, so that's 1 plus, apparently, I'm told for this particular theta, that's 5 squared. So in a minute, I think we're going to know what secant of theta is. Do you agree? So secant theta is either plus or minus root 26, which means actually, I know cosine, don't I? It's 1 over plus or minus root 26. Yeah? But it was told to us, I guess there's something else in the problem. It was told to us that cosine is positive, so I think we're done. I think we know cosine. Don't we? You see how the algebraic approach might be kind of slick there? If you know that this is true, then that helps you get cosine pretty quickly. It also asks for sine though, so maybe we're not done. So what other relationships can we establish? Well, I know tangent and I know cosine. Here's one. This is not the only way to do it, but I know that tan theta is equal to sine over cosine. That'd be one way to get this, maybe. And notice that I know everything in that equation, don't I, except for sine. So that'd be one way to do it. I'd like you to think about maybe there's maybe another way. 5 equals, so sine theta is equal to, what is that, 5 over root 26. Another way to get that would be what? Well, do you know any other ways of, I mean, how else could you get that sine? If you know cosine, you could maybe get sine, anything that relates cosine to sine directly? Yes? Yeah, I think just from the first Pythagorean identity, you could, if you have cosine, get sine, couldn't you? Right? Now, let's just recall how we did this before we had this technology. We're like, wait, we did this before? Well, we did. I gave you this problem before, but how did you do it? You didn't do it using this approach, that's for sure. Do you remember how you did it? What'd you do? You drew a triangle with a tangent, an angle that has a tangent of 5, and then you like computed the other sides using the Pythagorean theorem. So just so you know, if you work this problem a second time using the geometric approach, you will be using the Pythagorean theorem along the way. But I want you to understand that that's what the geometry feels like. Well, this is just the algebra. This is how the algebra feels, right? But you're making the same moves though, aren't you? This is how it feels algebraically. Before, I think we took a little bit of a more geometric approach, that's all. But in both cases, we're using the Pythagorean theorem to solve both. Here, now we're finally calling it like the Pythagorean identity or whatever, but whatever. It's still the same stuff under the hood, okay? Let's say something at least before, about the cofunction identities. Here they are. They're on your paper too. Now, the first thing I think you'll notice is that they do look a little familiar, but it makes you probably a little uncomfortable to see this. After the last unit, you're probably thinking like, oh, this does seem kind of right, but the way I would love to I'd prefer to see this, Mr. Chase, is like, I've just been doing a lot of graphing. I'd love to like think about this as being like a phase shift. I'd love to see this as being like a theta plus or minus pi over 2, right? So why is it written this way? And I have a good reason for writing it that way, I think. You ready? Because we're going to prove these too. Here we go. We'll just prove the first one. Here's an angle, let's call it theta. And for the time being, now actually this is not a full proof. You'll have to actually worry about the edge cases and different quadrants and stuff like that. But let's call this y and x and r. Okay. And let me ask you this: what is the cosine of theta? Let's write it down. It's just x over r. Do you agree? All right, now I have another question. What is this angle called? Up here. We could give it a name, but we could actually compute it. How would we compute it? Yeah, isn't this 90 minus theta? Or, since we've all grown a very strong affinity for radians, we could say pi over 2 minus theta. Isn't that angle there? Okay, so here comes the next question for you. Are you ready? What is the sine of that angle? Oh, is it the same thing? All the other ones feel the same way, don't they? So now I want to make sure you hear the names we called these too. These are called the cofunction identities. They establish the relationship between sine and cosine, secant and cosecant, tangent and cotangent. You see it? You see it? All right, more tomorrow. I think that should be enough for you to do homework 1 though. You'll do great.